Right, so last time we talked about the Antoine equation and how that was a measure of the pressure and the temperature when two phases of water, where it was the vapor phase and the liquid phase, were at equilibrium. And remember, we tried to reach the triple point, and we were able to do that. And then we also used linear and non-linear regression to plot models for the Antoine equation against or from experimental data that we had. But in today's video, we're going to be more focused on using those kind of concepts, especially that how the partial pressure of water vapor is equal to the water's vapor pressure, and how that sort of concept, and as well as some other concepts to solve a problem, but this time maybe not in the generic sort of uh, normal isolate one variable sort of way. In today's problem, we're going to be using all these concepts to try and creatively construct a system of relationships, and it is going to be nonlinear since we're going to have two unknowns, and you're going to see that in the problem once I pull it up. But we're going to have two unknowns, but just because we have two unknowns doesn't mean we can't solve it. We need two unknowns, or we have two unknowns, so we're going to have two equations. So we just have to use the values they give us in the problem, try to find as many relationships as we can to sort of try and solve the problem. And obviously, we aren't going to be doing it handwritten. Uh, Python is very nice and that going to be able to do this for us, but our job is to just create the relationships. So let's go ahead and do that. I'm going to go ahead and switch to my OneNote. All right, so this is our problem. We have an open container at 1 atmosphere. So actually, let's just start. Go ahead and write what we know. So at 1 atmosphere, there is 298 kelvins and 1 kilogram of liquid water. The container is sealed without removing the air, then heated to a pressure of 2 bar, at which point the vapor space contained 0.3 moles of water. And we have to solve for the final temperature as well as the total volume of the container. So, I don't know, let's go ahead and maybe try to visualize what we're doing. So it might look a little familiar. We have the same kind of open water or closed uh, air water system that we had before. In the previous video, when we tried to reach the triple point, we tried to push that air out, but we're going to have air up here and there's going to be water down there. And it is closed. So, and what we also know is that it's being heated up, I believe. Yes, heated up as it's going to change from 298 Kelvin, and it's heated up. The pressure also increases, so we have to find that final temperature. And to do that, actually, how do we want to do this? We have our water here. And if you notice, yeah, let's go ahead and start writing the what we know. So if you notice in the problem, they're actually given in different units. We actually want to keep them all in the same units. So our standard, we should use SI units. So let's go ahead and do that. So open container, so that pressure, initial pressure, 1 atmosphere. So I'm just going to go ahead and write that as 101.325 bars, or sorry, not bars, pascals. And that's the SI unit we're going to use for pressure. Temperature initial, they also give us. We have 1 kilogram of water. Kilograms is fine. Oh, sorry, that is temperature. That is my bad. Temperature initial, so 298 kelvins. All right, and then we have the kilogram of water. So let's just say, I don't know, water total. Since it is heating up, there will be water vapor. So let's just account for that. Just have it as the total water, since we know at the beginning there is 1 kilogram of water at the start. All right. So now we got all these. What else do we know? Heated to a pressure of 2 bar. So we know the final pressure. Okay. Final pressure, 2 bar. And that is about, if you do the calculations, 200,000 pascals. So just so we have same units for pressure. And then at which point the vapor space, so there will be vapor. Then we know that that vapor that vapor space contains 0.3 moles of water. So you can write that as I don't know, moles for n moles of water vapor, let's say. Moles of water vapor equals 0.3 moles water. Okay, and what we don't know here, what we don't know is the final temperature, and we don't know the total volume. Okay, how do we do this? We have a bunch of things we know and things we don't. Two things we don't. So let's just start with connecting the sort of obvious stuff, if that makes sense. Well, if there's a final pressure, and we know that vapor and air exist in the system, we can actually use ideal gas law, and that's just going to be one of the assumptions we make, one of the assumptions we make. As to make these relationships, we have to make assumptions in order to write down things we do know. So we do know about ideal gases that partial pressures exist because they act as if the gas, the gas exerts a sort of partial pressure as if it was the only one in that volume, in that space, and that is due to the fact that ideal gases, ideal gases, we assume we use ideal gases when there are high temperatures and low pressures, I believe. So high temperatures, low pressures. I mean, this is a relatively low pressure, so that's why we're going to use the assumption of ideal gas law. But so let's just keep on going what we're doing. So final pressure, we know that will be the pressure of the air plus the pressure of the water vapor. And if you remember, I'm just going to write it as water, but if you remember, I said earlier how the partial pressure of the water vapor is equal to the vapor pressure of the water. And that is because of another relationship we'll be using, very familiar, but let's just write the generalities for now. I'll come back to this later. So other generalities we know, okay, well, volume total, since we know it's going to be ideal gases, we can just basically say that the vapor phase at top, the gases that occupy that volume, and the volume occupied by the liquid water down below, that's just basically going to be our total volume. And if you remember ideal gases, how they don't see each other, we talk about how we ignore their attractions, their van der Waal attractions, as well as how we assume that they have negligible, they occupy negligible volume. And both those are going to be important. I guess moreover the part where they occupy a negligible volume, but we'll also come back to that. There's a lot of relationships we're going to be going through, so try to keep up with this. So volume total, we have our volume of our liquid water, and we also have volume of our vapor. Let's just call it vapor. Since we know it's going to be two gases, but we're just going to generalize to the vapor. All right, what else do we know from our knowns? Okay, we have our water total. And you remember that with the water total, we will have water vapor and liquid water. So there is just water at the start. At least in the problem, it says that there's an open container with 1 kilogram of liquid water. And since we close it, it's not like there's going to be more or less coming out since the system is closed. So we're going to use mass of the water total equal to our mass of the liquid and the mass of the vapor, since we know both exist at the end when the container is heated up. All right, those are the more obvious ones from this. So we're gonna have to try to look for more relationships that maybe aren't as obvious. So maybe let's just look at the unknowns and see if we can use anything. Well, we included our pressure. Okay, pressure is included. We have, let's see, we do need to include our temperature. So that's one thing we need to do. We have our mass included. Okay, we also have our water vapor included. So actually, let's go ahead and try to break down these more, I guess, not as obvious equations. I'm just going to call them like side equations. Not because they're not as important, but maybe because they're not as obvious. So Maybe, what do we know about mass of water total? Well, chemical engineering concepts, we know what mass of volume equals density. That's pretty obvious. So we do have the mass of the mass of the water total. So then this would be volume of the water, liquid water. And then this would be density of just water. So if we wanted, we do have this, so we can just set up an equation for this. All right, so let's go ahead and do that. I'm gonna erase this. Actually, I'll just leave it so we can see what we're doing. So let's isolate the volume of the water, the liquid water. So I'm just gonna say liquid water, and then we move it over here, and then move over density so we can have just volume on this side. Then we'll have the mass of the water liquid, the mass of the liquid water. How do we? I'll just keep on writing like that. Yeah, mass of the liquid water over the density, which we use. We do note that as the, I believe, Greek letter rho. So rho H2O, just density of water. Okay, so we have volume of the liquid, and if you notice, that does come into play right there. So we are making some more connections when we are looking at these side equations, so to say. Excuse me. So now, what else? We said we are going to look at the moles. Okay, how do moles come in play? Well, moles, if you remember, we have for mass of any given compound on, or excuse me, any given element on the periodic table, the mass is always, or is equivalent to the moles, excuse me, the moles over the molar mass. The mass is equal to the moles over molar mass. And what do we have? Moles. And we do know the molar mass of water. That is something we can find. That is a constant. So we can solve for the mass. And this is the mass of the water vapor. So let's go ahead and write that as well. So mass of the water vapor, right? So mass of the water vapor is what we're solving for. What do we want to? I kind of keep switching it. Let's just copy this for now, this kind of structure. So we have the substance, it's water. So mass of the water vapor is equal to moles of water vapor over molar mass. So moles, so we have moles of water vapor. See how I don't write the numbers initially, because once we're going to be putting this into code, it's very hard to keep track of all the numbers and what they mean. And when writing code, you want to be able to generalize and maybe possibly use that code in, for future solutions. So maybe just changing the numbers around. So every time maybe you want to apply this to a different problem with different numbers, you can just use a variable name and just change it as a parameter at the start instead of going in and changing every single number every time you do a different calculation. So that's just my philosophy with writing the variable names, as we were taught in MEB. But keep on going. We have the molar mass of water. Keep in mind we want we want SI units. So we know normally on the for molar mass we write it as grams per mole, but we should write it as kilograms per mole to keep everything the same. As you know, we have kilograms in our equation for relationships. So we know molar mass is around what 18.0 something grams per mole. So to convert that, we're just going to do times 10 to the negative third, and that would be 18. I'll just write it as 10 to the negative third kilograms per mole. And just so we can see how this checks out, it's just, if you remember dimension analysis, the units should cancel and leave you with the same units as what you're trying to solve for. So moles over kilograms per moles, you get 1 over kilograms, which is, 1 over kilograms, which is what we want over here. It's going to be moved over, so we have kilograms. Dividing by a fraction, multiplying by the reciprocal, you'll get kilograms. Anyways, what else should we do? Well, we have some relationships with our side equations, but we can actually keep on breaking this down. Since from earlier we noticed that on the side equation we were able to get the volume of liquid water, and we also derived the a relationship for the mass of the vapor water right here. Should probably just write this water. I need to be a little bit more consistent. Yeah, let's follow this structure. All right, so we have some relationships going on here that we can break down, I suppose. How do we want to? Do we want to keep breaking this down? We can. If you look over here, for the volume of the liquid water, we know it's equal to the mass of the liquid water. And we can actually isolate the liquid water and solve for the volume of liquid water by plugging in another relationship with this variable in regards to the main relationship it's involved in. So let's just write it out so you can see. I don't know what color, maybe red. So we have the volume of the liquid water. Keep in mind, we're just breaking it down. This isn't anything new. So volume of liquid water. What is the mass of the water, the liquid water? So mass of liquid water, if we move things over and isolate it, we have mass of the liquid water equal to mass of the total water minus mass of the vapor. So we'd be subtracting mass vapor from the total. And it makes sense. You have total water, you subtract the mass of vapor, and you'll be left with the mass of liquid. So subtracting from the mass total the mass of vapor over, this is our mass liquid, mass of the water liquid, over our density, which is rho L. Sorry, rho water. I mean rho L, I guess, for liquid. Okay, that's that. Can we break this down? I'm not sure if we want to just yet. You could also plug in the same thing for vapor, but this time in liquid. But it'd kind of be doing the same thing over here, which isn't exactly what we want, because as you know, if you start plugging in substitutions of the same equation into another equation in the same system, you're gonna get this. You're gonna be left with the same variables and relationships. You aren't gonna exactly break through with any new relationships because this is just part of this. It's not as if we made an entirely new different relationship. So let's just do just that. So we have solved for a little bit of the volume, but we also want to include the pressure that we're missing out right here, and or excuse me, the temperature. And we also haven't been touching the pressure as well. And as you know, that is because temperature is actually, we can actually relate that to our pressure. And how would you think of doing that? Well, you remember what I said earlier, this is a closed system, and we did assume that the gases were ideal gases. What does ideal gas tell you? Well, I hope there's only one thing that pops in mind, the ideal gas law. So PV equals nRT. We have pressure times the volume equal to the moles times the gas constant, universal gas constant, and temperature. And we can actually apply this to our pressure equations up here. So I guess I did underline how pressure of water is, but let's try. Yeah, I'll come back to that. I'll come back to that. So we have the pressure of air. Let's write that. Pressure of the air is equal to, pressure of the air is equal to, if we want to isolate it, we're going to have to move this over, but let's just start writing this. So, moles of air, and we want to specify that this is at the initial condition. And I'll talk about that in just a little bit, but we're just going to keep on writing this as why we use the initial, but we'll just keep on writing it. Moles of air, I mean, it is the same, so I guess there is no reason. I'll just keep it for now so you can see how it goes across the entire equation. So moles of air times the universal gas constant times temperature initial as well, because we're going to be using initial, and then over volume of the vapor phase. Now there is a reason why we're using the initial temperature, because we don't know the moles of air. We don't know the moles of air, and we can break that down a little further, but let's just focus on writing the ideal gases. And the temperature initial, like I said, the reason why we're using the initial conditions is because they go into play with how we derive a relationship for the moles of air. But if you remember in our system, we do have, it is water at the start. So, well, actually, you can probably see it better here. There is air and water at the start, and we close it. So the pressure in that container is 1 atmosphere, or 11325 pascals, but the air is also with the water, and like the water, it doesn't change. Like the water, it doesn't change since it is a closed system. Water and air do not leave the system, so we assume, actually more of we kind of know, that the amount of air that was there at the beginning is the same as the amount of air that was there at the end. But you can't exactly say that with water. You can say that with the mass of water, as there's no possible way for the weight to leave the system. But the mass of the water does change as some of it is going into the vapor phase as the temperature increases. So that is why we are using initial conditions, because this will also help us when we find a relationship for the moles of air. Let's keep on writing with the ideal gases. So we also have air, and our other gas, our vapor, our pressure of the vapor. And we can write that as the moles of the vapor times the universal gas constant. And we're going to use that for SI units, and because I didn't say that before, the 8.314, I believe, joules per kilogram mole, and then final temperature over our also the same volume of the vapor. And you remember, like I said before, the volume of the vapor, we assume that both gases occupy the same volume because they are ideal gases. Their volume, the amount of space they take up, is negligible because we assume they are ideal gases. And that overall, that assumption kind of goes a long way with us being able to write this the ideal gas law and make these sort of relationships. So we'll go back. We'll break this down, like I said. But before that, I also want to add that while I did write pressure of the vapor, this is also equal to the pressure of the water. And I should probably pick one so you don't get a little confused, but we know from the previous video, and also I believe I mentioned earlier, the partial pressure of the water is equal to the vapor pressure because both phases are in equilibrium with both phases being present. And that is also dependent, from our last video, we found an equation where the pressure of the vapor pressure was equal to the Antoine equation, which is 10 to the A minus, I believe, B over C plus T. And that is another place where we can relate a temperature to pressure. As you remember, that was the whole point of trying to find this relationship with ideal gases and related to temperature. You can see temperature being present in both equations. All right, so let's go ahead and keep on going. We're just going to keep on making as many relationships as we can so we can create the two equations we want for our two unknowns. We check on time. All right, so we're going to keep on going. We'll break down moles of air. All right, so moles of air. Maybe it should be different. Moles of air, let's see, pink maybe. Moles of air. What do we know? Let's just isolate it. Go ahead. Since we are using initial conditions at the start, you'll see once I write it out that it's very nice of why we use the initial conditions. So pressure of the air. Actually, yeah, pressure of the air. We can actually break that down. I'm gonna ahead and do it right now like we did here with here. But we know the pressure of the air is related to this equation up here. So we can actually write pressure of the air in terms of the final pressure minus the pressure of the water. So let's see that pressure, the final pressure minus the pressure of the water at the initial conditions. Isn't that a little weird? Oh, I know why, sorry. It's supposed to be initial because we are using initial conditions. So pressure of initial minus pressure of the water initially. Yes, right? Yes. So pressure of the water at the temperature initial. And then that is times volume. And move this over. Oh, I can, sorry. So it is volume, volume, pressure times volume. So volume vapor. We do know how to get the volume of the vapor phase. And I believe, where is that? Right here, volume of the vapor phase. We can isolate volume of the vapor phase equal to, same thing we did here, the total minus the liquid water. And we can also break down the liquid water into our equation of what we did know over here. And that's just breaking into more relationships and connecting them, and basically connecting them even further as we make more relationships with the equation. So we have our volume of the vapor phase, which is equal to the volume total, the total volume, minus volume liquid of the water, minus the volume of the liquid water. And we can break that down. Just draw the brackets so you can see. You can visualize we're breaking down volume of the liquid water, since we know that right here, which is the mass of the total minus the mass of the vapor water over the density. But we can't exactly do this, because if we include the mass of the vapor, we'll have to include another expression over here for why we're including the mass at all. So in order to generalize and make things easier for us, we're just going to be writing it as the mass of the, mass total at the beginning over the density of water. Now, does that make sense? Because volume of vapor is equal to volume of the total minus the volume of the liquid. And volume of the liquid, just like how we found here, is equal to mass over density. The reason why we don't use the mass vapor is to make things easier for us. And we can also assume in the problem that the mass is negligible, as there's no actual number for the mass vapor. So we assume it's a variable, or we assume it's not there at all. And to make things easier for us, we just assume it's not there at all. Now, you might be wondering why we do include the pressure of the water, since if the pressure of the water exists, there should be a mass that correlates to the vapor pressure. And again, that just comes with assumptions. Assumptions help us build relationships, but they also limit us in being as accurate as we can. So we will be a little bit not as accurate as we want to be. We won't be extremely on point, I guess you would say. So we'll keep on going, keep on writing these equations. So we isolated an air, moles of air. Everything's in the initial conditions, and then we just divide by universal gas constant times temperature initial. Now you see why we use the initial conditions and why they're so helpful for us, as we can build these types of relationships if and only with the types of assumptions we have made, with the ideal gases and how we assume the mass is negligible at the start for the vapor pressure, etc. And what else do we know? I think there's actually one more thing we do know. We can break the moles of vapor down. And why is that? Well, if you remember, we do have the moles of vapor. And if we break it down, we can have virtually this expression equal, well, not this expression exactly, but for that expression in terms of this equation, equal to a constant that we do know. So we do know the mass of the vapor. And I'm going to go ahead and write that out. I don't know, white maybe? Use, all right, cool. Moles of vapor, which we know is equal to 0.3 moles. You can write that and isolate it so we can have another relationship, basically. That's the whole goal. We want more relationships to build up so that we can get closer and closer to finding our two unknowns. So we have the volume, the moles of vapor equal to the pressure of the water, the final temperature, times the volume of the vapor pressure. The volume of the vapor pressure, the same up here. And I won't write it out, so just we save a little bit of time. And that will be over universal gas constant times temperature final. You can see I didn't break these down. Well, we know this was the same, but the more important reason why I didn't break down the pressure of the water at the final temperature is like how I said earlier, how I didn't break down mass of water liquid when I did for here for the volume of the liquid water. It's kind of useless to break things down more than once, as again, making substitutions of this from the same equation with the same variables involved will just bring you back to where you started. So, I mean, I guess you could write it, but there's not really a point, I guess, if that's what I'm trying to say. So it does come from, again, like I said, it does come from this initial equation, or not initial, it's actually at the final pressure. And this is the final pressure of the water, and this is the final pressure of the air equal to the total final pressure. But again, if I broke it up, it'd be the same thing. Right, so I think from here, we've actually gotten all the equations we've needed. And you might be wondering why. Well, that's all the concepts we know that can be applied to this problem. We applied ideal gas law, you applied moles molar ratio, or not molar ratio, molar mass, density even, ideal gas, I think I said that, and even the Antoine equation. So now we just let the code do the heavy lifting work, and assuming we don't make any syntax errors, it should be pretty easy. Hope that was recording. Cool. Okay. Let's switch on over to, I believe, hopefully this is open. Yep. Let's just switch over to our, we're going to start coding. And to do that, we're actually going to need something very special. Our Professor Carlos has made for us. Thank you again. We're going to use something called, he's coded a lot of things, as you probably would know or might have guessed, coded a lot of things to help us with this class. And something called in CHE Tools is one of his repositories on GitHub, and talked about GitHub in the last video. But we can use some of the code he's used. I think it is che.py, and yeah, it is a big beast of code. For at least for us for now, in terms of our levels of coding, but it actually will help us to access all these types of compounds that he has imported from ChemCAD. If you're familiar with ChemCAD, it is more of a simulation sort of. Actually, let's just look it up. ChemCAD. So ChemCAD. Let's see. Yeah, process simulation. So maybe at the upper levels of undergraduate work, we'll probably be using more of ChemCAD, and it's very important with just seeing how things will play out, because obviously we won't have access to those chemicals or compounds at all times. But the more important thing that we're using is importing. He's imported all, I think some 35 compounds that their physical properties and their chemical properties, and those will help us in solving for our water equation with water. Yeah, let's just go ahead and do just that. All right, let's go back on collaboratory. I don't know, let's just open up a new notebook. If you remember, collaboratory was just the free Jupyter notebook. You can write Python on your browser. Again, mentioned that last video. I won't go too deep into it, but it is very nice for just simple coding at ease of accessibility. I'm gonna take. So we've been talking a bit. All right. So let's get to it. What do I want to call it? I don't know. Let me move my tablet. Let's say closed. Oh, that should not be there. Closed water air system. Water air. That's fine. All right, so what we're gonna do to access this code in GitHub, we're gonna actually have to use a underlying operating system command. Again, the exclamation mark is back, and if you remember from the last one, we used wget to get web content from the server. But in this case, in order to access the code, and use the functions as well as keep the Git operations accessible and still functional. We're going to use git clone, and that kind of goes into the whole Git software, or let's just look it up. I believe they help with coding in terms of being able to push out code and receive code, edit code virtually, and pretty much just like that. But with wget, we won't exactly be able to use the same types of things unless we did clone the repository. And I'll just say it now, using wget would just pull that data or the code from the repository in GitHub, but it wouldn't keep the functionality of the Git operations functional. You would basically just have some local code stored on, I guess, on Collab, but you wouldn't really be able to use anything like git push or I don't know the other Git operations. I won't get into it, but basically, we do want this code, CHE tools. All right, so we go to we go to the code. Make sure you see this. Okay, go to the code. We copy that. And this is just remember the URL that we're going to use. Same thing or similar to wget, but we're gonna clone the code that comes from this repository that Carlos has made for us. And I'm actually just gonna go ahead and put this in. It is death1, this line of code right here. And it's basically just telling, so in GitHub, it stores our all the histories of the code, all the different versions and changes that were made. And if we were to just git clone it and just clone, we would clone the entire thing of all the version histories, and obviously that's not something we want to do. It's just this little line of code just makes it slightly faster. Again, it's probably not, it's minimal. You probably don't even need it since it does download pretty fast. But yeah, I guess let's just go ahead and evaluate it. So it's gonna go ahead and clone it. And if you remember when we used the exclamation mark, they did always go into our file manager, and now it's done. It should appear. Nice. Right, so in order to use the modules from his repository, we're gonna have to change how the how Python looks through all the directories in its files right now. So we're gonna import the system and tell the system in its path, and the path has it's just this huge list of directories with all the different places that we'll store our files, and we're going to insert on that path at the front of that path. Let's see, where is this? We are in, I believe, content. Yeah, CHE tools, that's what we want. So we're going to go ahead and store that at the front. So content, CHE tools. Spell that right. CHE tools, and run that bad boy. Cool. So now that we've inserted our we've inserted our module, or I guess his code, Carlos's code for us to use freely in this in our little notebook. So what do we do next? Well, I guess we should. I guess we can import. Yeah, let's go ahead and just import the code that he has. Oh, that's not what I want. How do we get back? So we're gonna import. So from content and CHE tools, we go to his tools, and like we said earlier, these are some code that he's written. We want the che.py. That is for the Python code that we're gonna copy and use, or I guess import. So we're how do we want to do it? Import in the tools. So import tools and .che for the module, and we want to import that as CHE so we don't have to type tools.che every single time. And now that should go ahead. Yep, shift enter. We've done that. All right, so now inside CHE there is a class called prop. So we're going to be doing something called we're going to be making an object. I'll just call that object P for now. But for this object, we're going to have to, I believe, what is it? Instantiate a class called props. I'm going to instantiate the class called props to make our object. And this is just, props is for properties of the list of compounds you saw at the start. So I don't know. We'll do water for now. I mean, we will be using water. And we shift entered. So, okay, warning. So we don't actually have to worry about this. Carlos has actually optimized this code to be able to run on a GPU. And since it's not actually running on a GPU, it says no GPU found, falling back to CPU. That's fine. It's just gonna run on our CPU. And really, you'd only see the difference. I guess maybe not so much at the coding we're gonna do right now, but in terms of bigger, longer, like more difficult computations, uh, with coding, you do want, if you can, using a GPU makes running that code a lot heck faster, basically. And I guess the analogy I could come up with is maybe you talk about, so say the CPU is like the brain. I would say GPU is kind of brawn, but stick with me in this analogy in the sense that CPU will be able to, it is a brain, so it can do a lot of computations by itself. It'll just pull it and come back. So think of it maybe as a on-demand plane. So it'll be able to go ahead, drop things over to where it needs to go, one at a time. Now, the GPU, you'd think of that as a cargo plane. And as the brawn, it basically stores up a bunch of things it can deliver all at once. And the idea of that analogy is that the GPU can do a lot more heavy work lifting at the same time versus the CPU. Now, that's not all too important with what we have. It's just another little aside I wanted to mention so you don't get too worried about this. So in this object we've created P, we can now access all the properties that Carlos has imported from ChemCAD. So if we go back to data, I don't know, water. Let's see, where's water? Right there. Open that up. You look in here, and it is a lot of properties that we may or may not ever use for, I don't know, in this little videoing thing we got going on. But it has things like look, Antoine vapor pressure, liquid surface tension, liquid viscosity. I don't know if we can find it. We're going to be using P.Pvap, which is vapor pressure right here, and it does come from equation number 101. So if you remember, Antoine equation is what we used last time to determine a sort of relationship between the pressure and the temperature. But ChemCAD is using a slightly more, I guess, sophisticated equation making system in that they have, I guess, more parameters. Well, actually, you'll see. We'll go look up it for ourselves. So equation 101, ChemCAD. So they basically just use a more sophisticated equation. Oh, where'd it go? Should be somewhere here. Right here, equation 101. So you can see it, 1, 2, 3, 4, 5 parameters versus the A, B, and C that Antoine equation uses. And that just makes it a lot more accurate because we aren't doing it by hand, we aren't plugging in. It's the computer doing it for us, so obviously we want it to be as accurate as it can be. So if we do P.Pvap as a name of that, I don't know, and if you remember vapor pressure, this little equation is dependent on, is a function of temperature. Yeah, temperature. So we can just go ahead and plug in, I don't know, 0. That's our temperature, and it is in Kelvin, I believe, or Celsius. Does it? It's Kelvin, right? Yeah, Kelvin. And it will give us the vapor pressure in Pascal. So this returns us our value. Oh, I guess maybe not. Did I do this correctly? Oh. Maybe we use a bigger number? There we go. There, we got a number. So 273.15. I guess it would be reading that as absolute 0 if I wrote in 0. But so 273.15, this is our vapor pressure at that temperature in Kelvin, and our pressure is in Pascal. So nice thing about this object, not only does it let you work with multiple properties that you can call all at once, you don't have to do these individual calculations and run things like equation 101 every time you need to use it. You can also use a list inside this object that we can use to access multiple compounds at the same time. The reason you have to use a list is, well, actually I can just show you. If I try to add, say ethanol that I just wrote, if I try to add ethanol, try to reevaluate the function for PVAP, for pressure of the vapor, it'll only give me the same number for water. It'll only be one number. And the reason for that is because it's not exactly reading ethanol as part of the object for when it's calling all the properties. So now if we run again, we should have, yep, second number right there. Nice. So that is the amazing thing about this code that Carlos has written, or I guess coding in general. You could run multiple types of components, compounds in a mixture, let's say, because that's what chemical engineers do. They work with mixtures. So you're working with mixtures that have all these different types of compounds, and you have to use all these types of properties, but you don't have to do any of the calculations. You just have to set up what you want, and all of the individual ones that are for the individual components will come up as soon as you just code them correctly. Easier said than done. All right, so let's go back to our original problem. Just go ahead and delete this. Yeah, go ahead. We don't have to delete the list, but I'll just delete it anyway. So, our original problem, we're going to be using the coding in Collab to try and, using the coding in Collab to try and solve our nonlinear system that we made back in my OneNote with that problem. How are we going to do that? Well, if you remember last time when we solved nonlinear systems, we used a function. So I'm going to go ahead and define that function, not sum squared error this time, like I almost just typed. We're going to be using, I don't know, what do you want to call it? Equations. It's just two equations that we're going to be using, but we will be writing a lot of relationships. I don't know, equations is fine, I guess. And then equations, and it's going to return us this vector. Let's just type vector so we don't get confused with volume later on, but a vector. So we're going to be using this function that returns us the vector of our unknowns and trying to find using the root function, or I guess, is it a function? The root from scipy.optimize, if that sounds familiar. That's from scipy, where we use minimize for our sum square errors, minimizing the sum square errors. This time we're going to be using a root to solve for the unknowns that we have in our equation. So our unknowns, what are they? Temperature final and volume total is equal to our vector. And let's just go ahead and import, so I don't forget, from scipy.optimize, import root, not minimize, root, shift enter, make sure we got that. All right, and we want to return our temperature and our volume. Well, the fun thing about using root is, here, I'll show you an example. Let's say root finds things when they're equal to 0. So temperature final, let's say we want it, we're just going to make up numbers to see if it can solve it. So temperature final, I don't know, is equal to 20. So if it's equal to 20, you have to set it to 0 in order for the root to be able to solve it. So we'll just subtract 20. Same thing on this side, where let's just put parentheses. Temperature final minus 20, and then maybe volume total, just so we can see a difference. I don't know, minus 100. Enter. Water. Oh, excuse me. So now that we have this function, two unknowns, and two equations, we can use the root function, a function of our, I believe it's a function, root of our function equations, and we're going to return, well, we have to provide an initial guess, and that's just for whenever you're solving a nonlinear system or just using root, you want to apply some sort of accurate initial guess so that the root goes on the right path and converges to the correct solution. Otherwise, it might just not do that at all if we don't give it sort of right pathway. So we know the temperature is 20. Let's just say it's I don't know, we guessed and said it was 15, and then we also guessed for volume total, maybe we said it was 150. We're going to go ahead and evaluate that. Okay, so it does give us 20 and 100. So it did solve the equation we had, right? So to solve the equation we had, now we just have to apply this. It's the same sort of concept that we're going to apply to our system. We're going to solve for something when it equals 0, our unknowns when it equals 0, and it'll try to give it a good guess, and hopefully it works out. So let's go ahead and do just that. Oh, and also just another thing to as an aside for the root at this first values, or I guess this first list of values it shows up at the start is basically, I believe, the number of times it's tried to. Moreover, you want them equal to 0, as close to 0 as you can possible. See, if I get closer and have the correct answer, maybe they should, in theory, go to 0. Yeah, pretty much. You'll have -1, 0. You want them pretty close to 0 because that's what a root does. The root solves for when values are equal to 0. And again, same vector or same values it returns because again, this equation is pretty straightforward. So we're gonna head and do that. So what do we want to do? What do we want to equal to 0? Well, our relationship with temperature was with pressure. Here, I'm actually gonna show. Sorry about that. All right. Let's go back to the browser. Okay, sorry about that. So we're gonna be setting, like I said, setting some equations to 0. That's how we will use root, but we need to figure out what we're gonna set equal to 0. Well, if we remember, going back to our equations in our OneNote, you're gonna have, I believe, where is it? We did say the temperature is related to the pressure somehow. So going back to that, we'll have to use that relationship in our unknown right here. So what do? We do pressure final minus the pressure. Well, I guess it makes sense if I write this like this. Pressure final equals the pressure final that we want, right? That's how it's going to be equal to 0. Because we want the final pressure to be what we say it is. And it's going to solve for that final pressure, if that makes sense. All right, so that it satisfies that equation. So we're just going to do subtract, so that is equal to 0 now. And the same thing almost over here, volume. How is volume related? Well, volume is, we use moles to relate that to our, volume. The moles come in here. We have moles as a condition, and we're setting it equal, or we're going to use it as a relationship to build for finding the volume total. And you can notice how I use the things in the initial conditions of what we know into the two equations that we want. So that's our moles. What was I doing? Pressure. So we're just using pressure. I guess it's just these pressure, I guess more over final pressure, but that's fine. So I used our initial conditions to set up the equations, the relationships that we're going to be using for our code. So same thing here, similar. The moles of the vapor phase equal the moles of the vapor phase that we want. So I'm going to subtract that, make it equal to 0. I'm just going to underscore it. So we go ahead and just know the difference. And now, what do? We start writing all the relationships we know. Well, what do we know? Let's define all the parameters we know. So, I don't know, pressure initial equals, what do we say? SI units, 101.325 pascals. Let's see, temperature initial is 290, was it 298? Yeah, 298 kelvins. I should probably comment that out. Kelvins. Mass of the water total, or just mass total, is equal, let's make sure we know. Mass of the water total is equal to 1 kilogram. And the final pressure, we know that, or I guess desired final temperature, since it's going to be solving for final pressure over there, it is 200,000 pascals. I put enough zeros? Yeah. Okay, 200,000. 1, 2, 3. Okay, 200,000 and also our moles of vapor. So moles of vapor desired, since that's what we want, 0.3 moles. Do you see what I'm doing? Okay. And let's go ahead and put the gas constant in right there while we're at it, so we don't forget. 8.314 joules per kilogram mole, I believe. Kilogram times mole. Okay, cool. We got all our parameters set. Shift enter, make sure that's in. I think those should be good. Okay. What else do we know? Go back. I think that was all our initial conditions. Yeah. I might be wondering over here, the pressure and Antoine equation. I did briefly mention earlier, but with that new code that Carlos coded for us, we can actually use the more sophisticated equation I showed you earlier, equation 101 that ChemCAD uses. Again, that's for computer heavy work. We don't have to do any of that. It's just nice for us to be able to pull that without doing this actual calculation. Instead of doing the Antoine equation, we can actually just do P.P.vap to give us the pressure of the vapor every time we want it. I guess anytime we want it, every time we're going to use it in our equations. Right, so now we're going to define all the relationships we need to use. Well, I don't know. How about we solve for the moles of vapor first? Because we know that, right? We know our moles of vapor is equal to, go back and see what it was. Moles of vapor is equal to, right here, we have pressure of the water at its final, the final vapor pressure at the final temperature, excuse me, the volume of the vapor divided by the gas constant times the final temperature. We're going to write exactly that. Pressure of the water final. So we can actually just, since we are going to write that as the vapor pressure with P.P.vap, I don't want to write it as that every single time when we're going to use the final temperature. So let's just go ahead and define it at the top right here. Define it as P.P.vap. I would be writing that down there, but just for shorthand, we can do it up here. And notice from here to here, we can just write that as the vapor pressure at the final temperature. And then we can just keep this as is. See the highlighted. And pay attention to those highlights, because you want, whenever you're going to use a variable, you want to make sure it's defined before you use it. So we defined moles of vapor there, and it is the pressure of the water at the final temperature times, I believe, vapor volume of the vapor we use as VV, volume of the vapor phase, and let's space that out so we can see it. Volume of the vapor phase, so N VV over RT, so divided by gas constant times the final temperature. Notice how it's final temperature. Okay. We will be using this at the initial temperature. Let's just go ahead and do it. So we'll say this is final. You can see pressure of the water final. Pressure of water initial would be the same thing almost, but at the lower temperature. And remember, we're using temperature inside the function because the vapor pressure as a code in the function is written as a function of temperature. So we have to give it the argument of temperature. All right, what's next? We have moles of vapor. Well, pressure of the final pressure, excuse me. So final pressure, it was going back, a lot of going back, right here. Moles of air times this big expression. And I think we can probably leave it out as VVAP if we wanted to. In terms of this part right here, we could just write it as volume of the vapor and define volume of the vapor later. But actually, that's not the right spot. We're actually over here. Sorry about that. Pressure of the air, or final pressure. I don't know. Oh, that's actually not right here. Sorry, we are pressure final is right here. I can't read today. Final pressure. Final pressure is just our first equation. So final pressure is equal to final pressure is equal to pressure of the air, oh, where'd you go? Pressure of the air plus the pressure of the water. And that was at the final temperature. So we use final, pressure of water, final. All right. Well, we defined these two. Let's see what we can define from here. Looks like we're missing the volume of the vapor. That is equal to, volume of the vapor is equal to, volume of the vapor. Where is that? The volume of the vapor phase is, trying to find it, somewhere right here. Oh, did I say vapor? It is vapor. Sorry about that. Volume of the vapor phase. Where did we find out? This is liquid water. I believe. Oh, I'm sorry about that. We can actually rewrite volume of the vapor phase like we did here, but should actually be. Let's go ahead and write it so you can see what I'm talking about. Volume of the vapor. Since we didn't know, I guess I glossed over it. Volume of the vapor. We used the volume total equation. So volume of the vapor, is A, sorry. Volume of the vapor equals volume total minus volume of the liquid, where we can break down liquid since we do want, in our equations, we want to define them going up, and we're kind of working backwards to see what we need to define. So we can just keep this as volume liquid if we wanted. All right, so going back. Volume of the vapor phase is equal to volume total. Where did you go? Volume total. A lot of alt tabbing. Volume total minus the volume of the liquid. And I believe, does the volume of the liquid depend on, I think this should be fine. Volume of the liquid. You do have to be careful when writing a relationship, since you don't want to define a variable that'll need something that goes after it. So sometimes you can just write the lowest, I'll call it the lowest equation. Oops, sorry about that. It's my alarm. Lowest equation. And just write it as is, so we don't have to keep substituting. We don't have to define a variable that requires another variable. You'll see. I think we're good. We'll just have to find out. So pressure of the air. Go ahead and define that. Pressure of the air. Going back, we said pressure of the air. Remember, at the initial conditions, pressure of the air, initial conditions, moles of air times the gas constant times temperature initial, because the moles of air are the same. So we use initial conditions, which allows us to define what the moles of air are. So PV divided by VVAP. And again, this is actually, see what I did? See, if I try to write this, it'll give me an error. Let's see. We'll say it's defined. Oh, guess not. Well, you want it to be defined after the fact that you did volume of the vapor. So see this as in, make sure it's, when you use it on the right hand side, make sure it's defined on the left of the equal sign. So we did that. What are we missing? Pressure of the air, water. We have that. We have the initial, the vapor. Go ahead, let's just break it down so we don't have to write them as much. So V liquid, if you remember, we use density. So mass of the liquid over mass of, I believe, the density. And again, we're using, it's similar to the PVAP, vapor pressure. We're using rho L, if you remember, the density, the Greek letter for density, rho L. And then our temperature, which is the final temperature since it's vapor. And we don't have to write parentheses for that. We shouldn't. What else should we do? Define volume total, perhaps? Volume total equals, should be able to let us go for it since we are solving for volume total. Keep in mind how, yeah, like we are solving for volume total, but that doesn't stop us from using it in any of these equations. So volume total, volume vapor phase, okay. What are we missing? I don't know. We have moles, we have final pressure, pressure of the air, vapor, Is it all that's left is sounds like the moles of air left, and also the moles of, well, we do have the moles of vapor. So I guess we can just go ahead. I think there's something missing, but we're just gonna have to go and find out and see if we're close. And I'll go back if I did make a mistake. So let's find the moles of air. Moles of air is equal to, again, this is initial conditions, so pressure initial minus pressure of the water at the initial, so I should probably make that an I. And the reason for this is because pressure of the air is the pressure, initial pressure, minus the vapor pressure of the water in the system. That's what we defined earlier in our OneNote. And using initial conditions is how we're able to derive for moles of air, which is why we use initial conditions down here for pressure of the air. So pressure of the air is then broken down into the initial pressure minus the vapor pressure of the water at the initial temperature, and then times the volume of the vapor phase, which is, we can just write it as, I guess it should be below that, huh? Well, let's just write it as is. So volume total. VVAP is the volume of the vapor. So we're using that for air because, again, ideal gas, we assume it occupies negligible space, and we use the same volume for both the vapor and the in the air, like we're doing right now. And so we put in the volume vapor, which is equal to our volume total minus mass of the liquid over density final temperature, and that is representative of the vapor of the liquid, because we remember that vapor of density is the relationship between mass over volume. We're solving for the vapor of the liquid for this part to subtract from the total volume. So we do mass of the liquid over the mass, or the density, density of the density of the water at the final temperature. And I think I just remembered what we were forgetting, but we'll just finish this right here. We have volume vapor done, and then over our universal gas constant times temperature initial. And if you are having trouble following where I wrote these are just from what we wrote. I'm alt-tabbing, if you can tell, probably from the sound of my keyboard. But yeah, what you want to do when solving these types of problems, you want to write down everything you know, and eventually, once you write down everything you know, you'll be able to find an equation, or two equations in this case for two unknowns, or for solving the type of problem that you're going for. And this is very different from how we normally solve problems like this, where we can't just isolate the variables. See how I'm even using the unknown in a relationship? It's definitely different from anything I've done in high school. So, but this is the type of problems chemical engineers will encounter with multiple components, multiple relationships, multiple unknowns. So we're just going to keep on going. And then we did forget to include our moles. So how do moles come into play? Moles should be related to volume somehow. And the moles we can define as the mass of the volume. Let's see, where did we use it? That should have been used for, I believe, the mass when we were doing, let's go back so you can see what I'm doing. The mass is, this was our volume, or this was our moles. We want to relate this somehow. We can't just leave it out since it is a relationship we derived. I believe we can use this to solve for vapor moles. And I think we did do that. So we can, I think, let's see here. Moles of vapor, we had that equal to 0.3 in ideal gas, but we can also relate it to the mass of the vapor water. Oh, you know what? We didn't do the mass total, which is very important. And this M liquid, the mass of the liquid, does come into play with that. So we can go ahead and define that maybe above the moles of air. Let's go back so you can see. So I'm going to, you can see how they're highlighted. It's not related at all yet. So we're going to do mass of the liquid. Mass of the liquid is equal to, see, mass of the liquid is equal to the volume times the pressure. Is that how we want to do it? Volume of the liquid. Volume of the liquid. Volume of the liquid times density is rho L. P dot rho L over liquid is just final temperature. I don't think that's right. Volume of the liquid equal. Did we use the liquid at all? We should use it when we define the total volume. Maybe we should put this up here. So V total equal to, V total is equal to volume of the liquid. How do we want to do this? It is, see how the relationships get a little bit more complicated, since you have to keep in mind you want to write variables that are already defined. And since I can't write, if I have to define these, they have to go over. It's weird because these should be, this should be the last thing we define, as it has nearly all the relationships we know. Tell you what, I am going to find out the mistake I made and explain it once I am done. Alright, sorry about that. I think I found my mistake. If we go to our code here, right here, I actually had this typed out with the, I was a little confused and got confused because I didn't know where to put our relationships, but we remember that the moles of air is equal to the pressure of our air, which is found from the subtracting the pressure of the water initially, the vapor pressure initially, from the initial pressure. That leaves us with the pressure of the air. Okay, that makes sense. Here, I got a little confused, put final temperature in here, but we remember that this is at initial conditions, because at the start we have a closed system. We have air, and that air doesn't leave. It's the same once we close it. It's the same at the start and at the end. And that's what's letting us make these connections between our initial conditions given in the problem. So we want the volume at the start, or volume at the start, which is given from subtracting the volume total minus the volume of the liquid. And we actually can break that volume of the liquid down over here. This time we're actually going to put it underneath. I'll show you something how we can still use it up there. But volume of the liquid, I believe it was, oh, hold on, that's actually not right, because remember this is the initial conditions. We're not accounting for the mass of the water vapor. So we actually have to use the mass of the total mass of water. And is it, oh, it's MW total, sorry. MW total over the density of water, which is the P object, and then rho L, which is the density, and then that is at temperature initial. And we remember that I said that we were assuming that the mass of the water vapor was negligible at the time, even though we do use the relationship of pressure of the water being subtracted from the initial pressure to get the pressure of the air. And again, one of the assumptions that we use. But this volume of the liquid subtracted from the volume total to give the volume of the vapor, which is the same for the air because they were ideal gases, and we said the volume is negligible. This is not the same as this volume of liquid, that this equation is not the same as the one I'm about to use here, even though they are both technically accounting for the volume of the vapor. But this volume of the liquid that I'm about to write is actually this one right here. And I guess you don't really need it, but for my sake, I guess we're gonna write it anyway. So we can just see where it comes from. Just like how we broke apart each step going up, with what we needed. So we had moles of vapor, we made that here. Okay, final pressure, we got that. And then we needed, this was just the, excuse me, the pressure of the water vapor. This is the volume of the vapor, which we describe right here. It's just constants. Again, just going up and trying to find out what we need and putting our relationships to it. Go slow. I guess I went a little too fast for my sake, since I got a little lost once I started writing them. But okay, so we've got our volume liquid, and we've fixed our moles of air, and now we still have the squiggly line. The nice thing about collab is that it's highlighting what we're missing in our errors. So we still need to define the moles of the liquid, which, if you remember, we'll go back to our OneNote once more. Mass of the liquid, liquid water, we could have derived it from, remember, it is the density formula. So we can just rearrange this how we did before with the volume of the liquid. Excuse me, we rearranged it so that we can use our constant up here. I believe it was, oh, it's not up here. Well, let's just go ahead and do it. Yeah, let's just write it as is so we don't have to. Yeah, let's go ahead and do that. It is mass of the liquid. Mass of the liquid, it'd be volume times the density. So that's exactly what we're gonna write. Volume, oops, volume of the liquid, which is volume liquid times the density, which is P object rho L, and that will be at the final temperature. All right, I think we've got all our relationships. Just click through, see if they're here. This, remember. Oh, yep, okay, I guess it was a while, so I'll just go ahead and factory reset everything. Make sure everything runs well before we start trying to make sure we got the right answers. All right, it's running. Remember, we cloned it. We got our code. Oh, and here, this isn't wrong. Okay, so we got an error. VTotal is not defined. Right, because we did not define VTotal as the volume total. Actually, this should be rewritten, I suppose. Well, that's not true either. What did we do again? Looks like I will have to go back one more time to find out exactly what was missing, unless it is just spelling, possibly. Right there, yes sir. Volume total is underscore. Or not, V liquid. Here we go, V liquid before assignment, right. Oh, right, here's what I was talking about earlier when you don't want your variables on the right to appear before they are defined on the left. So a quick way we can actually get rid of that, let's see, we can try to, let's check if that's right. Volume liquid, yeah, that's our density. Mass, oh. You know what? I think I mixed up mass of, I mixed up one of these things because I remember we're not using our molar mass. So how are we gonna fix that? Volume of the vapor is equal to the volume total minus volume of liquid. That's good. We need to define our volume of the liquid, and the volume of our liquid we established was equal to mass over density, which is fine. We need to somehow define our moles, which our moles were defined, our mass of the water vapor is equal to the moles over molar mass. So either we can define molar mass, or actually we have moles, so we need to define our mass of the water vapor. And that does not appear, it looks like, here at all, which is quite peculiar. Yeah, this definitely, I just rewrote this, which, like, it's kind of doesn't really help us with anything. So let's change that. We want to make our mass of liquid equal to, we need to define our mass of liquid, I guess we should say. But our mass of liquid, all right, let's just go back and think about this. We have our mass of liquid. We want to somehow define this equation back into our other relationships. And that comes through here where we could have substituted the mass of the vapor in the volume of the liquid derivation. So in our volume liquid, let's see, did I mistake again? Oh, okay, yeah, volume of the liquid. Okay, I guess my code is just completely wrong. At just this one part, again, we had this little not so, it doesn't really change our relationship, so it was just rewriting this equation. But now we had volume of liquid is what we want, and we could change that, going back to our OneNote, change that by putting this equation in, and then putting this here. So let's do that. Volume of liquid is mass total minus mass of the vapor. Okay. Let's switch back. Volume of the liquid equals the mass total. Mass. The water total. Let me sure you get it right. Mass. Well, okay. Mass, water. Yep, that one. And then minus our mass of the water vapor. Mass of the water vapor, which hasn't been defined, which is good because we're going to do that next using our moles, moles over molar mass. And that is all over the density of water. That makes sense because we know the volume of the liquid is simply mass of liquid, or sorry, we know we can derive the volume of the liquid from the density formula where mass is over volume equals density, and we isolate volume to have mass over density. And then we just broke down that mass of the liquid is the water total minus the water vapor. And that makes sense because if we know the total at the start, but when the system increased, the temperature increased, the water kind of split off into a little bit of water vapor. So now, excuse me, now some of the water, initially that was 1 kilogram of water at the start, is now, some of that mass is now into water vapor. And that is our volume, or sorry, excuse me, that is our mass of liquid. And we said that was over density. Mass over density equals our volume. Again, using the P object. I believe I explained this before, but in case I didn't, it just calls the properties that we are using. And this is density, which is a function of temperature, as Carlos wrote in his code. So we are calling, I believe this should be final temperature. Yes, because it is a liquid and it's dependent on final temperature. All right. What's next? We need to define our mass of water vapor because it's squiggled over there. Mass of water vapor. And we could just write it, but we're already here. So mass of our water vapor, we can now use our moles over molar mass, which is our moles of water vapor. Moles of water vapor desired, what we initially had, or will have, I suppose, given the sequence of time in the problem, but it is our moles of vapor over our molar mass, which is 18 times 10 to the negative third. And that was because that's just a molar mass. We know grams per mole is around 18, so we just multiply it, or I guess divide, sorry, by 1,000. Yeah, 3 zeros. 1, 2, 3. Yeah, 1,000, sorry. To get our SI units. That should be around right, and our guesses are completely off. So let's go ahead. I don't know. Maybe we use these guesses. I believe it was 0.1. Oh, too many values to unpack. What happened? Expected 2. The comma? Oh, I see. That is a period. Here we go. All right, that's pretty nice. We can see that. Oh, okay. So it is pretty close to 0, but the values we are looking for, this is our, I believe, temperature, final temperature, and volume. It should be kelvins and we use cubic meters and turn that to liters. So that's about what? 70 liters. This is 0.07. Yeah, 0.07 cubic meters times 1,000. All right. So that is our final answer. We have around 378 Kelvin at the final temperature of the system once it's heated up to what we said it was in our parameters. Once it was heated up to, where was it? Do we even have our, well, it is the final temperature, sorry. This is the final temperature, 378 Kelvin, resulting from the initial conditions of the gases, or sorry, the initial conditions of the pressure being equal to 101,325 pascals, the temperature initially being 298 Kelvin, and the initially being 1 kilogram of mass of water total. And then this was our final pressure that we had. It was 200,000 pascals. And with the amount of moles at the vapor phase for 0.3, these two were the both the temperature and the volume as a result of those parameters. Now, the nice thing about Python is that you can actually rewrite your code to solve for, say, we didn't know, I don't know, we didn't know moles, but we had one of these. So simply, but easier said than done, you would rewrite your relationships in order to have, you would have your moles as an unknown up here, and then you would have one of your, what was this, volume? Yeah, volume. Then you would have your volume minus your volume desired here in order for the root to solve for 0, since you have your initial volume, assuming they give it to you, you have your initial volume equal to what you wanted. Would that be, I mean, it could also be, I guess it'd be total volume in this case. If we flip those around, we'd have total volume here equaling our desired, and we'd subtract it to make it equal 0 again for our root. And yeah, that is the nice thing about Python solving the root even with all these relationships. And it'd be extremely hard to solve for this as a nonlinear system by hand. You could and start plugging in everything you would know into this this equation. You'd start plugging in, well, we have PF here. Instead of going backwards and defining what we didn't know, you would just substitute it into what you did. And with that, I think that it's worth to mention the notability of these guesses. I think I mentioned it earlier as well, how your guesses can influence whether or not the root will be able to converge to a solution or not. But let's say I didn't pick this, we won't be extremely close to 0. Let's see. We can actually evaluate this, and it should just give us, okay, I guess it's not equal to 0 at all. Maybe... Okay, it's just, oh, I see what the problem is. We need to evaluate just our function at, yep, here we go. So that is not even close to 0, but it was as close as we were going to get, even though I believe it should be around 10 liters, so 0.0, yeah, 0.01 for cubic meters. And I think it was like 360 Kelvin was the temperature, but we can actually manipulate this around to see if we can get something closer to 0, since that's what we want, and those would give us our values for final pressure, or sorry, for total temperature, our final temperature, and our total volume. So maybe, I don't know, 275, 115, I don't know. Did I go up or down? I couldn't tell. Okay, that is way too high. So we are close at around 15 probably. It is getting pretty close. 275, I don't know, 290. Now we're over. Oh, that was 390. So maybe 340. Maybe 375. And again, this is what the root is doing. It's changing your guesses in accordance with, until this will equal to 0. And changing this probably will also affect whether or not your values are equal to 0. And I could caps lock enter. Yeah, so that becomes 520 instead. We'll keep that at 0.1. Maybe, I don't know, 390. I guess I can come back after doing this for a while and see if I can fix our guesses to probably make this our numbers here more accurate. Here you can see that the numbers like sort of explosively get closer and closer to zero as I change our guesses. That's because there is only one solution, and it will go very quickly to zero once you're close enough. And I really swear I was getting right there. Yeah, it's kind of boring to do this. Oh yeah, it's almost like exactly there. Maybe you can modify this a little bit. That's too far, so maybe you want another zero. We're getting there. We're really close. Alright, I think that's as far as we're gonna get. So let's probably try just copy pasting our guesses into here. And maybe we'll get a better look at our numbers. So yeah, it did change. It actually it did decrease. The volume did decrease closer to, I think I said earlier was 10 liters. Now it's about 40 liters if I'm doing the math right. That's 0.04 cubic meters, which goes, you did some unit conversion that becomes 40 liters, and this goes up 380 Kelvin. Again, the guesses really do affect how close you are, and I'm pretty sure this number is a lot closer to zero than our other number was. I think it was to -4th. Now it's -5th, so even smaller. And that's what we want our guesses to be, very close to our solution. It's a sort of guided guess, and that's sort of what makes distinguishes a good chemical engineer from another, is being able to know the right guesses of what to put in. Yeah, that concludes this video. Or so I thought. We actually have a little mistake here that we can fix. And these numbers in our calculation that are integers right now. And what we want to do is change them from integers to floats. And the reason why we want to do that is because with integers, what Python actually does with integers is that it does a little bit of rounding off, which we don't want and leads us away from our accuracy. But we want to make sure Python is running our code as accurate as possible. So, which is why I'm changing all these numbers, what I'm doing right now. I'm changing all these numbers from integers to floats with the decimal point. And that decimal point actually tells Python that we want them to be accounted for as floats. And that should be all our numbers. All right, and you might be asking why I'm not changing this -3. That's because it is a in the exponent, so we don't have to worry about it. But make sure everything gets evaluated this time. We want to do Shift-Enter for both, and Shift-Enter. And we can actually go back to our initial guess we used before, way back. I believe it's 315.01. Make sure we add the decimal point there, because the guesses are also part of the code that Python runs. And Shift-Enter everything. We should get our numbers. So this is actually 366 Kelvin, if you remember our temperature final. And then this is volume, so that's about 0.01 cubic meters, which is about 10 liters. And yeah, that should be the real end of the video.